Okay, so last month we released Android 7.1 Nougat, and it has a whole raft of features for audio developers, and I'll hand over to Phil to talk about some of them.
Okay. One of the things that we looked at was the Java latency. Down from 200 milliseconds down to around the 25 to 30 or less latency range, but the Java was still very high, and that was because there were some extra buffers that the Java was going through that aren't really needed anymore. They used to be needed because the garbage collector would interrupt the Java threads for quite a long time, but that's greatly improved. So we added a flag for the Java audio output, which is this flag low latency, and if you turn that on, you bypass this extra large buffer and you go directly to the fast mixer. So that eliminates about 40 to 90 milliseconds of latency just by turning on this flag. So that's a big jump. And so what some people do now is if they have synthesizer code written in C++, they'll go ahead and call their C++ code through JNI, harvest the audio, and then actually just write it out through the Java audio track, and then they don't deal with OpenSL. So some folks are doing that. Or if you're writing just a pure Java application, sometimes people were forced to use native code just to get the audio performance. But now you could write sort of the entire app, including your audio code, in Java and get reasonable performance.
Sorry, quick kind of straw poll. How many of you use Java? Half a hand. Okay, two halves make one. Okay, just interested.
I won't spend a lot of time on this slide then. In case you do, or if you have friends who program in Java, and this technique, you can actually do something similar to this with OpenSL now. The buffer size that's allocated in Java now to set the effective size. So if you have a 4K buffer, you might set the effective size at 512 or 384, and that becomes what determines your latency. So if you never fill the buffer beyond this small threshold, you don't pay the latency cost of having all this extra audio in your buffer. But if you fill it too low, then you may get underruns. And so what you can do is you start off your process maybe with a low buffer size, and if you get underruns, you keep bumping up the effective buffer size until the underruns stop. And then at that point, you know that for that particular platform, you've got your optimal latency without getting underruns. And that'll vary from platform to platform. So rather than having to know, oh, I'm on this phone, I can get away with this much latency, you don't know. There could be other background tasks running. So this way you can dynamically tune that. And you can do the tuning just when you're playing silence. So the user is not going to hear a bunch of glitching. This can happen just as soon as you start the audio, boom, you tune it, and then you're there at the optimal latency point.
Cool, thanks. So one of the other features we introduced in Nougat was this sustained performance API, and this came about because we realized that performance can fluctuate dramatically for long-running apps. I mean, typically what you would see is on an audio app running which has a very high computational load will run for maybe a couple of minutes, and then the device will go into a thermal throttling state where it has to scale back the CPU frequency in order to let the device cool down. Now, this creates a user experience where it's fantastic, 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 terrible, and that's not great, obviously. So we created this sustained performance mode, which gives you two things. It gives you an exclusive core, so there's no latency introduced by core migrations, where your application thread is shifted from one core to another, and it sets the upper bound for the CPU frequency. So some of you might be thinking, hang on, this is a performance mode, but you're reducing the CPU frequency. Well, the emphasis is on sustained. So you reduce the CPU frequency and you reduce the chances of running into thermal throttling issues. There are a few caveats with this, which is it's only available for the foreground app, so as soon as your app is backgrounded, then you're going to lose these privileges. and there's no lower bound for CPU frequency. So you'll still be affected by CPU frequency scaling. More on this a bit later on. So what does it look like in action? Well, here I have a system trace from a Nexus 6P device, and on the left-hand side you can see all the cores here, and we can see that. So we have cores 0 to 3, which is on a Nexus 6P is a Cortex A53 CPU, and then we have cores 4 to 7, 7's off the screen there, on Cortex A57 CPU. So our application is running on core 0 at the top here, and it has a clock frequency of 1.5 gigahertz. And if we switch sustained performance mode on, see we're still running on the same core, but we've been dropped down to 960 megahertz. So this gives us a much better chance of running for a long period of time without running into this thermal throttling issue. I mean, it depends on your environmental settings as well. Like, if you're running in a 50-degree desert, then this is not going to help because you'll hit thermal throttling whatever you do. But in normal environmental conditions, sustained performance should give you a consistent upper bound for CPU frequency for a long period of time, like minutes or hours. So, more in the hours than the minutes, I would say. The other thing to notice here is that the A57 CPU has been completely clocked off, so it's not even on. And the reason for that is because it's a much higher performance CPU, we just switch it off entirely because basically it generates too much heat. Sorry, any questions on that? Great. One of the other things we've done in Nougat is to fix a bug that was introduced in Marshmallow, where the number of buffers in OpenSL was always 1. So it didn't matter what you set, whether you were attempting to do double buffering, the underlying audio framework always just used 1 on Nexus devices. So this led to audio glitches. We fixed that. Now Nougat has more reliable audio. Phil, you've been doing some diagrams on this.
Yeah, so this sort of shows the, in an architectural sense what some of these changes are involved. So this, in the shared memory area, you can see this extra buffer that the Java code had on Marshmallow, but in Nougat you can bypass that, and then we can also inject our audio sort of into just the bottom part of the buffer so we can get the lower latency. And then in OpenSL you can see that there's just that one buffer there in shared memory, so the fast mixer is reading from that buffer. And even though there are more buffers that are being used, they're not available to the fast mixer. So if the fast mixer, if the client code is stalled, the fast mixer will run out of data. But with in Nougat you can set up a double buffering or more buffers if you need to, and that gives you better glitch protection in the fast mixer.
So what else have we done recently? We launched some new phones. You might have seen the adverts. So we launched the Pixel and the Pixel XL. Both of these conform to the Android Professional Audio Standard. That means that they have sub 20 millisecond round trip audio latency over the headset. In tests that I've been running, it's around 16 milliseconds. They also support USB audio and MIDI. They both have a 3.5mm headset jack. Yeah, various other specs here. In terms of latency, like, we're really making a lot of progress when it comes to latency along various different parts of the signal path. So around 10 milliseconds for output latency on the new Pixel devices, input about 2 milliseconds, MIDI 1, touch about 30, Bluetooth latency about 7.5 milliseconds, the minimum possible on any device, even on desktop. And in order to demonstrate this, I actually have an app here, if I can just switch over here. Right. Great, I just exposed my pin to everyone. Right, so I have a DJing app here. This is eDJing Scratch from DJ It. And I also have a connected Bluetooth crossfader here. So, if you notice here, as I move the crossfader, you can see this tiny little line here moves left and right. Now, I'm sorry, the latency on the screen is actually really bad. So if you look at my hand, you'll see, there's probably, I don't know, 500 milliseconds of latency there. There we go, right. So I've got a backing track. Let's just switch to that. Oh yeah, the latency on the audio in here is also too bad to run through the audio system, so you just have to listen on here. So I've got a track here which I can fade off like that and bring back in, and I've also got a sample here, which if I move this in, you can hear that, but it's actually much more interesting if I start this, and now I can cut the sample in.
Check this out.
Yeah. So there we go. The really cool thing about this, I mean, I'm no scratch master or anything like that, but
No.
evidently. The really cool thing is it really is kind of indistinguishable from like an analog mixer. I have an analog mixer, so it's really cool. I mean, if you're into DJing or turntablism, you can genuinely use this for like cutting and scratching and flares and chirps and all the rest of it. So yeah, the latency is pretty great there. So on the topic of latency, so we have done a lot to lower latency over the past few Android releases. And we kind of see this like big, like large amount of latency as a plaster that we were kind of hoping when you pull the plaster off, there'd be no problems underneath. But in reality, you might find like a festering mess of technical problems underneath.
Some new
Oh
challenges.
yeah, some new challenges rather. So some of the challenges that we have on Android, as well as low latency, is giving developers predictable CPU throughput. You always have to have enough CPU throughput available to create interesting sound. Like no one is interested in having a low latency sine wave, especially if that sine wave also has audio glitches in it. So in the past, we've had tests for all of these things. We test for artifact-free audio. We test the latency, and we test to make sure that there is CPU throughput at a given point in time. What we haven't been testing is all of these things together working for a long period of time. So that's really our focus now. And one of the key things that we've been focusing on, which I'd like to talk about, is CPU frequency scaling. Now, it was funny in the talk yesterday from David from Raleigh, who basically had the exact same slide with the same wording on it independently, nothing to do with us. So CPU frequency scaling is like the number one issue when it comes to developing on mobile, especially on Android. I mean, just to put this in context, CPU frequency scaling is kind of a great thing for users because it enables users to have fantastic battery life, but also performance when they need it. They don't want the CPU at maximum frequency whilst the device is in their pocket. So it does give this like great trade-off between power consumption and performance. The CPU frequency scaling algorithm on Android is influenced by user interaction, and we call this touch boost, where you tap on the screen and the CPU frequency increases. And it's also influenced by the current CPU load. So see this in action. I have another systrace showing the CPU frequency at the top here. User stops touching the screen about 1 second. Half a second later, the governor will scale the frequency down to about half its original clock rate. And down at the bottom here, you can see the status of our audio buffer. And these gaps indicate audio glitches. So you see, as soon as the frequency drops, our app is suddenly unable to meet its audio deadlines and starts producing audio glitches. The other thing which affects the CPU frequency is the current application load. And Phil, you've been running some tests on this, haven't you?
Yeah, so we have, in part of this new SynthMark benchmark that runs a simulated synthesizer load, where each voice is kind of like a subtractive synthesis load, like it's sort of like the number of mini mogs that you are calculating at one time. And what we see is that initially, as you start adding more and more voices, the CPU load goes up linearly, and it stays linear as long as you're at this sort of minimum clock frequency. Once you start to get up around 75 or 80%, suddenly that curve just turns over. And the reason is because the CPU load is a function of the number of voices divided by the clock frequency. Voices, the governor sees your load increase, and it just keeps increasing the clock frequency. So those will stay together, and you'll sort of be like just plateau at this roughly 80% of CPU load, and you'll stay there while you go from, in this case, like 25 voices all the way up to 90 voices on this particular machine. This is kind of a hypothetical machine. Until you get to the point where the CPU frequency is at a maximum, and then at that point the governor can't do anything for you, and then you go back into a linear portion here, and you just stay linear until you get up to 100% CPU load. So actually I was feeding into
So the key point here is that the governor wants to keep you at round about 80% load. That's where it sees things are most efficient, which is fine unless you have an algorithm which always focuses on a specific CPU load which is less than 80%. Now, we actually saw this with an initial alpha of Raleigh noise. So here's a typical scenario, and this is actually quite a common strategy for app developers to look at targeting 50% CPU load. I mean, it kind of makes sense. 50% for your music app, 50% is left for the system to do whatever else it needs. It seems like a reasonable compromise. But here's what actually happens. You target 50% CPU load. The governor looks at your application and goes, aha, there's some performance power consumption optimization that we can make here. We're going to scale down the frequency and increase your load to 80%, which is fine. But then your app spots that you're now using 80% load and scales down the number of voices that it uses back to 50%. And you can see we go around this, we call it a spiral of death. And what this ends up in is the lowest possible CPU frequency, and typically, well, in the case of noise, monophony, which is not like the best user experience. So what can you do about this? Firstly, this sounds really obvious, but start with the number of voices you think you'll need, based on device testing, and don't cut that number of voices unless you're hitting 90%. Like, if you stay above this 80% threshold, the governor's absolutely fine with everything that you're doing, so it's not going to scale your frequency down. Try to keep the CPU load constant, for example, by gating voices on and off, rather than shutting them off entirely. Double buffer, this protects against audio glitches, and if you can, use sustained performance mode. Any questions on this? Yeah, go for it.
Is there not an argument for an API that allows the program to determine how much of the potential, CPU usage at whatever the highest frequency is? If you had that number as a sort of fixed number, couldn't you then use that to target your kind of voice?
Yes, there is. I mean,
absolutely, yes.
Yeah,
and I'm glad you said that, because now I can go back to the system performance people and say developers are asking for an API that will allow them to, yes. Because what happens now is that, is it okay? Oh,
yeah, go for it.
What happens now is that there's this sort of statistical monitoring of your application, and let's say you're double buffering and you're hitting these deadlines, boom, 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 and suddenly you play a chord and your number of voices increase, you suddenly go from like 80% to 160% because you double the number of voices. Well, you're going to miss your deadlines. But by the time the governor sees that you're doing extra work, and it'll ramp up your clock speed, but it doesn't happen immediately. By that time, you've already glitched, you've missed your deadline. So the application usually knows, if they get the MIDI information in, they go, oh, I'm going to go from 4 voices to 8 voices. I know that I'm going to double my CPU load. They could inform the governor that they need that, and the governor could could switch much more quickly in time for you to not miss the deadlines. So I'm glad you asked that. I will relay that request to system performance.
This is something that we're actively working on. So, yeah, it's a great suggestion. Any more questions? Yep.
Do you have a case where you're toggling between two switch points up and down in your governor, and then what happens is like it is do you do some sort of hysteresis management to the governor so it will not jump from one point to another in such cases?
So the question is, why is the governor performance so or behavior so erratic? Is that
Yeah.
Or does it oscillate or something?
It oscillates a lot, and it seems like it oscillates from the same point.
Yeah.
A lot, because you can go up and then immediately it will lower the number of voices, and then it will go down according to that, and then it has to do with the magic
feedback
circle
cycle. Yeah.
So the way the governor is implemented is OEM dependent, as in so Samsung has their own, Nvidia has their own. So it depends is the answer to that. But we can control it at a framework level to a certain extent, and in the guidance that we provide to OEMs. And our ideal strategy is to have a governor which maintains a fairly constant CPU frequency, tailing off kind of gradually as the user's not doing much. But then when the user, 10 keys down on the keyboard, ramps up within nanoseconds, rather than the case at the moment, which is like tens of milliseconds it takes to ramp the frequency up. And this is all like the power consumption performance trade-off. So essentially it's about putting forward the case of high performance audio is a use case which we want to support, and we do want to support. It's just about getting those engineering features into the framework itself, which is something Phil and I are both working on. Sorry, my screen's gone off. Does that answer your question?
Partially, yes. Thank you.
Okay, any more questions?
Another thing we've seen with the governor is that if you have a task and you distribute it across more than one thread, so let's say you have a task that is just burning the CPU up and using, running as fast as it can. So if you just run it in one thread, the CPU governor will see that, this task is using all the CPU and it'll ramp up your clock frequency. If you split that task between two threads, because maybe you have some decoding happening in one thread, you have a pipeline, like a media pipeline, and the task is distributed across multiple threads, which sometimes people do if latency is not a big issue. The governor will see that and say, this task is running at 50%, this is 50%, they've got all the time in the world, and it'll lower the clock frequency, and then that task will just take a very long time. So be aware that that the governor may not recognize that the tasks that are split between threads are really one task, and so that's something to watch for.
So in terms of what we are doing, so what are we doing about this problem, which we kind of already talked about. So we have a better testing system. We have this SynthMark is a internal testing tool at the moment, but the plan for it is to open source it as a cross-platform synthesizer that benchmarks performance across a whole range of devices. We also have two hardware-based latency testing applications, both of them on GitHub. That's Walt and Loopback app. So if you are interested in doing latency testing for your app, then please get in contact with us and we can supply you with the hardware. We actually have these, the hardware manufactured to give out to developers and OEMs to help them do better performance testing on their devices for high-performance audio use cases. We just released much stronger guidance for Android OEMs in the CDD, which is the compatibility document, and that includes guidance on how to do sustainable CPU performance, clock drift, latency across a range of different signal paths. So, and that's published online as well. And yeah, working on a better Android framework. So all the things that we've talked about, we're aware of, and we are trying to address them. And I just kind of want to say that now that Google makes hardware, these Pixel phones, we're finally in a position where the software people can talk to the hardware people because they're in the same place, and we can start making progress on these like high performance use cases because we have a much closer connection between software and hardware. So that's quite exciting.
Yeah, and then the hope is that then once we have an example of showing what the high performance audio system can do, then other OEMs can emulate the Pixel phones. So hopefully all these changes will propagate through the ecosystem.
Okay.
Also, I have a demo of a pure Java synthesizer running with low latency, and it shows the effect of the tuning. If people want to try that.
Any questions?
Well, you
Fabian.
just mentioned Phil with the two threads. I found that very interesting. I mean, if Team was talking, I think it's happening right now, is going to be talking about log-free, log-free queues and like never log on the audio thread. So it's quite common actually to have two threads. Often the one thread may be reading something from disk, or I don't know, doing some other stuff that then feeds into the audio thread because you don't want the audio thread to log.
Yeah.
So I don't know, would that be considered by the governor? Like if you have these use cases, and which also the noise app does, to like feed the samples, it will have another thread reading the samples from the SD card, I guess.
But are you reading the discs like sort of in real time when they hit a note and you go and you read this, or are you just loading when you're loading?
Yeah, well, yeah. In that case, we have another thread actually just touching the samples all the time so that they stay hot in cache.
Okay. Yeah.
I mean, I think many audios
you-
do use two threads for lock-free programming, so that the
Yeah.
audio thread stays lock-free.
Right. If you using the FIFOs and using the lock-free is a good thing to do if you do have the threads, and pushing your I/O into the thread is good, but just be aware that if you're doing a lot of work in the decoding, if it's just a matter of doing the I/O, then it's not really CPU bound. But if you're doing a lot of decompression, and you're pipelining that, it may take a long time to load up a bunch of samples. And so if you're just loading stuff into memory, if you can fit all that into one thread, then that loading task will be quicker if it's in one thread. Done.
Cool. With that, thank you all very much for coming. See you later.